Okay, good morning. Let's get started from where we left last time. So, we were seeing basically what are the different types of timing constraints that we have to deal with when we try to develop these real time systems. And we had seen that deadline is a popular constraint, very frequently occurs, but we will also have delay constraints and duration constraints. And we had said that we need to model these for various reasons. One is to understand these constraints better. The second is that we can generate code from this, and I was saying that there are many tools being used in industry where the model timing constraints and automatically generates code for them, right. So, let us see now how do we really construct the models. So, we had seen that it serves as a formal specification, can be used to verify the behavior and to specify the behavior of the system and the environment accurately, can be used to automatically generate code, and also it helps us understand, get insight into the behavior of the real time behavior. And we had last time said that we will use extended finite state machine for modeling the timing behavior. So, this was the basic syntax that we had mentioned, that two states, if there is a transition, is annotated with the event which enables the transition to take place, and then some actions that take place while the transition occurs. So, the first thing we are trying to model last time is a stimulus deadline constraint, or the deadline existing between two stimulus events. So, the example we had discussed from the telephone domain is that once a user completes dialing a digit, he should dial the next digit within the next 5 seconds, otherwise idle tone will be produced. So, let us see how the model will be constructed. I think we are just seeing as last time that once the first digit is dialed, set a timer for 5 millisecond, and then we will await the second digit. I think somebody mentioned this, we just corrected here, we written last time first digit, corrected it to await second digit, and then once the second digit comes, it awaits the next digit and then the next one, and so on. And some of you had mentioned that we can use a loop here, but I was telling that if we, since the digits are finite, just 8 or 10, we can even model them the different states here. But if the timer alarm comes before the second digit could be dialed, that is 5 millisecond has expired, 5 second actually, it is not millisecond, 5 seconds have expired before the digit is dialed, then as soon as the 5 second expires, we will get the timer alarm and it will transit to await caller unhook and produce the idle tone. So, the idle tone will keep on producing until it enters the unhook, or the handset is replaced on the telephone. Now, let us see how deadline constraint between a stimulus and the corresponding response can be modeled. So, the example that we are considering is that as soon as the dial tone appears, you lift the handset and then after some time the dial tone appears, and as soon as the dial tone appears, then you must dial the first digit within 30 seconds. Otherwise, it will just enter into an idle state and a beeping tone will be produced. So, very similar, the dial tone is produced and it enters the await first digit state, and we set the timer for 30 seconds, and okay, here there is again a problem, no, it should be first digit, sorry, yeah, first digit, This should be the first digit, it is not the dial tone. Dial tone has produced and that is why it has entered first digit, and once the first digit appears, it should go to next, await next digit. So, this should be the first digit, and if the first digit is not dialed and 30 seconds have passed, then the timer will fire, the timer alarm event will occur, and it will produce beeping until the caller replaces the handset. Now, let us see the other example we had considered, that is deadline of a response from the corresponding stimulus event. So, here once the receiver is lifted from the handset, then the system must produce the dial tone within 2 seconds of lifting the receiver, and in case the system cannot produce the dial tone, then it will produce a beeping sound and the handset has to be replaced and dialed again. So, the caller has lifted the handset, and then this is the event, handset lift event, and 2 second set timer. So, we are modeling all timing constraints through timers, and we will see that when we do programming also, we will use something similar, real time programming. So, it is awaiting the dial tone, and if the dial tone appears, then it enters the first digit state, and if the timer expires before the dial tone could be produced by the system, then the system produces a beeping sound, and until the caller replaces the handset. Now, let us see the other example of a deadline of one response event from another response event. Once the ringtone is given to the callee, the ringback tone must be given to the caller within 2 seconds, otherwise the call is terminated. This is the example we had seen. So, after the digits have been dialed, the ringtone is given to the caller, and once the ringtone has been given to the caller, the timer for 2 seconds is set, and it enters the await ringback tone state. And if the ringback tone is produced by the system, then it this is not await first digit, actually there is a mistake here, it just enters the call state, right, ongoing call state. There is a problem here. Actually, I had just copied the other diagrams and just modified them in each slide. So, I forgotten to modify this one. Now, if the ringback tone could not be given, then the call should be terminated. So, the timer alarm has fired because 2 seconds have passed and the ringback tone could not be given to the caller, and it will terminate the call, and it will also produce idle sound. Possibly we could have written here call is no, it is not mentioned here, but if we had mentioned here that call is terminated and also a beeping sound is produced, then we could have also written here timer alarm, and then the actions are terminate call and beeping, and it continues in this action continues until the receiver is replaced on the the handset is replaced on the phone. Now, let us see the delay constraint modeling. The example that we had taken for delay constraint is that once a caller dials one digit on the telephone, the next digit should be dialed at least after 1 second. If it is too quickly dialed, then there will be error and beeping sound will be produced until the caller replaces the handset. We are just saying that in the our conventional phones, it is difficult to really dial too fast within 1 second. It is not within the human response time anyway. The only problem that might occur is that you press 2 keys at the same time or something. or maybe in very quick succession, just one after other. So, let us see how this will be modeled, a delay constraint. So, again we use a timer here. So, the first digit has been dialed and we set a timer of 1 second, right, and then it awaits the next event or awaits the next digit, and okay, here also there is a problem actually, not written it properly. So, if the second digit comes, okay, so if the second digit, timer alarm is all right, if the second digit comes here, this should have been second digit, right. If the second digit comes here before the alarm, and then it should go to await receiver on hook, it should produce a, it should not terminate call, it should actually produce a beeping sound. I am sorry, here both are these incorrect, I just did it quickly. The timer alarm it should be have been the second digit, and the terminate call should have been beeping. Now, let us look at the duration example. This is actually more involved, because there are several types of deadline and delay constraints involved here. So, the example of the duration that we are discussing from the telephone domain is that if the button is on the handset is pressed for less than 15 seconds, it will connect to the local operator, and if you keep on pressing the button for more than 15 seconds up to 30 seconds, then it will connect to the international operator, and any press more than 30 seconds, if you keep on pressing for more than 30 seconds, then it will produce the dial tone. So, this is the duration that between 0 to 15 connect to the local operator, between 15 to 30 duration it will connect to the international operator, and 30 more than 30 it will connect to the, it will produce the dial tone. But how do we model this duration constraint? We will have to first identify the deadline and delay constraints involved here, and then we will have to identify the constraints are for which events. So, let us look at the model and then try to answer these questions. So, see here, okay, I am sorry, again there is a mistake here, it should have been button release, right, instead of button press. See, you release the button on the handset, that is what is written here also. I am sorry, yeah, that is okay, it is okay, it is okay. So, button is pressed. So, you have lifted the handset and you are pressing the button, and if you keep it pressed for less than 15 seconds and try to listen, it will connect you to the local operator, between 15 to 30 international operator, and more than 30 is the dial tone will be produced. So, let us see the model. So, this is all right, you are pressing the button and setting the timer for 15 seconds. So, this if the button release occurs, so this is the deadline, the button release occurs between 15 less than 15, then it will connect to the local operator, local operator state will be reached. But if the timer alarm comes, that is a delay of 15 seconds, after the delay of 15 seconds, it will reach the await event 2, and in await event 2 we have a deadline here, just see here, by if before 15 seconds the button release occurs, the deadline is 15 here for it to reach the international operator state. Now, if the timer alarm occurs, that is again another delay of 15, then if the timer alarm comes here before the button could be released, then it will await the button release for any time that you keep it pressed. There is no limit, that is what it said, more than 30. So, keeps on waiting here until you release the button and the dial tone is produced after you release the button and it goes to the dial tone state. Now, let us try to do few small examples. Let us see if you can do. Please do it neatly, I will just show it here. So, first example, simple one. The temperature of a chemical reactor when the temperature of a chemical reactor rises above some threshold T degree centigrade, let us say, then the heater needs to be shut off within 5 millisecond of this event occurring, otherwise the plant is shut off. Just a simple problem, modeling problem. Let us see using the syntax and the concepts that were discussed, that timing is modeled using a timer. Let us see if you can do this. Please try. So, is this a deadline or a delay constraint? What do you think? It is a deadline constraint. Okay. The heater must be shut off within 50 millisecond. It is a deadline constraint, and if the deadline cannot be met by the system, then the plant is shut off. So, is it a performance constraint or is it a behavioral constraint? What do you think? Yeah, it is. See, there is nothing to really think of too much, because it is on the system event that whether it can shut it off. Some event has occurred in the environment. Environment is basically temperature exceeded for some reason. So, can the system be shut off within 10, or can the computer there controlling it produce the event to shut it off within 10 millisecond. So, it is a constraint on the system event produced by the system. So, it is a performance constraint clearly. Now, let us see whether you are able to draw the model. So, as soon as you draw it, please give it here. Anyone who completes first will just display it, so that the others can see and give their comments, if it is correct or if there are any difficulties there. So, I hope the problem is clear, simple problem. Done? Okay, great. Let us see. Yeah, what is your name? Sorry? Bharat. Bhanu Prasad. Okay. So, let us see what Bhanu Prasad has done. Can it be projected? Let us see if it shows up. Okay, it is actually showing very small, but still let me just read out so that you can see here, that the way he has done it here is that the event is temperature above T degree centigrade, and then he has a set timer. The action is set timer and is set it for 10 millisecond, and then what is this is not labeled anything. So, does it go to a state or is it just a, it is nothing here, that is what he says. So, if the timer alarm comes, then the plant is shut off, but what about until the timer alarm, it stays in the header, what is this? Heater shutdown. It stays in heater shutdown, and then once the timer event comes, the plant is shut off. doesn't look all right. I mean, what do you think? So, what is the problem here? Anybody has done it different way? Yeah, please. Yeah, give it. So, let us see here. Actually, for this to be projected, maybe you should draw it slightly larger. Okay. So, let us see this. I am sorry, what is your name? Srikanth. Let us see what Srikanth has done. So, if the temperature is greater than T degree centigrade, but this is a condition, no? It is not an event. Okay, event of temperature greater than T degree centigrade. Set timer to 10 millisecond and then it enters a state called as E1. And then if the sort of heater event occurs, then it heater off state, is it? Heater off state, and on alarm it shuts up the plant. Okay, plant sort of event. Okay, looks more acceptable, but one thing is that, see, the states we should give meaningful name. We could have given await heater sort of. That might have been. Let me just redraw his what he has drawn there. Let me just redraw that here. So, one is the event is high temperature. High temperature is the event, and the action is set timer to 10 millisecond, and once the high temperature is sensed, it awaits heater shut off, await heater shut off. And if the timer alarm comes before the heater could be shut off, the timer alarm event comes, then it goes to the shut off state. On the other hand, if the heater shut off signal could be generated to the corresponding sensor, then it goes to a heater shut off state. Heater shut or something. Does it appear okay? I am sorry.
The other one is plant shut off.
Plant, okay, shut off plant. Yeah, right. Yes, plant shut off. Yeah, plant shut off. Yeah, that is a more meaningful name here. Plant shut off, and this is heater shut off. But we have given the event name here, heater shut off. So, I just tried to give a different name here. Heater off state. Okay, yes. Heater off state. Okay, that is a better name here. Heater off state. This is just a simple deadline like we were discussing the other examples. Telephone domain is something very similar to that, right? Is that looks okay, or anybody has any difficulties here in this model? Because if you are actually developing real time systems programming, many times you will have to actually develop this using some tools. For example, the Simulink state flow, I think he will tell you about that. There you model the states, and on the events on which the state transitions occur, the timing, all those are modeled, and that actually generates the code. So, there are many tools like that, which once you create the model, it will generate the code for you. Not on, yes.
But in this diagram, no heritage wells and temperature greater than T.
Okay, yeah. See, let us see here this question. He says that high temperature, how does this capture that this event is generated when the temperature is greater than T degree centigrade? Okay, possibly we can mention here that high temperature is the event that gets generated, the event occurs once the temperature is sensed to be more than T degree centigrade. So, this is the name of the event, and temperature exceeding T degree centigrade is actually the condition, right. Temperature exceeding, temperature greater than T is a condition, and if that condition is satisfied, then high temperature event is generated. Now, let us look at another example. Let us see if you can do that, possibly slightly more complex than this one. Please take your notebooks. So, this is an example of a wash machine. Here we need to identify the time constraints and model them. So, the behavior of the wash machine is as follows. If you press the start switch on the wash machine, then the stirring will commence. So, you put clothes etc., water is filled up, and then once you press the start switch, stirring commences, it continues until a timer expires. So, before pressing the start switch, you should have pressed the time, you should have set the timer, otherwise possibly it will be a default value, and then it continues stirring until the stop button is pressed by the user. We could have also alternate example like the water filling in the wash machine occurs as soon as you press a water fill, and the water filling continues until the high level is sensed for the water in the wash machine, or the user presses the stop button. So, please try this one, because many times even the concepts and the terminology is simple, unless we do one or two problems, we do not really get a feel of it. Very similar to the previous problem, just small modifications in the model. Please try. So, please draw slightly larger so that we can project it. So, Srikant again has completed earliest. Let us see what he has done. So, again not very visible, but let me just read it for you. So, once the start event occurs,
it occurs on pressing start switch.
Okay.
Description.
Okay. So, start event is the event that occurs when start switch is pressed, that is all right. Now, set timer for the default value. We can write some preset value T or something. T is a preset value, and T is either a default value or it is the one set by the user. And then if the stop event occurs or the stop switch is pressed, then
Stop the machine. The action is stop the machine, or the state will be stop state.
okay. The action is a stop machine and it enters in a stop state. Okay, all right. Now, if the timer alarm occurs before the stop could be pressed, and then stop machine signal is generated. So, these actions occur by the system, is not it? Stop machine is action by the system, and this the event, stop event is by the user, and here it again enters the stop state. We could have also used the same state. two states, yes.
Stop, timer alarm. The events.
Here stop machine and timer alarm, is it?
Either stop or timer alarm. Means the events, two events.
No, that's okay. I am saying that state can be one and you can have two transitions occurring here. Possible.
One transition we can keep two events labeled.
No, that will be confusing. I mean, how do you have two events on one transition? That you can do. Each transition is enabled by one event. So, let me just redraw that since it is not looking very clean here. So, let me just copy his model here. See, one is it enters the steering state. Once the start event occurs, and the action that takes place before it enters the steering state is set timer T, where T is the either the preset, I mean the one set by the user, or it is a preset, it is a default value. And then if the timer alarm comes, then it goes into the stop state, and you can write the action is some stop machine signal is generated. And it also enters the stop state if the stop switch is pressed, stop pressed, and again the stop machine signal is generated by the system. The event is by the user, whereas the action is by the system, and then it again enters the stop state. Does that appear all right? Any difficulties here? Okay. So, let us proceed further. So, let us not spend time practicing more problems, because if we are able to do simple problems, then possibly we can do more complex problems with a little bit of effort. We have to just identify the timing constraints and then identify the states, and then model the, I mean find out which transition event causes the transition, and then the action that takes place, and that is about it. Right. Now, let us proceed further. Okay. Now, let us look at some very basics of task scheduling. We have looked at the timing constraints, and we are saying that the main means adopted by any operating system, real time operating system, is task scheduling to be able to meet the timing constraints that are specified. So, let us see what are the task scheduling techniques here, and how are these different from the task schedulers you had studied in a simple, I mean first level operating system course. So, we had seen that the events that we are concerned about are either the ones that are generated by the environment or those which are generated by the system, right. We will call them as internal or external events. And we had just seen the example of an event getting generated on a temperature exceeding some value, and this is the event which is generated by the environment. And when the event gets generated, the operating system, it will enable some task, right. Tasks have been programmed, written the program, and there are handler events, we will see later, and that will just enable that task, right. So, as soon as the event occurs, the task will be enabled, high temperature handler task will start, and as soon as the task starts, we call it as the task has been released or task has arrived. We will use this terminology. See, every area has its own terminologies, and we will use this kind of terminology, that the task is released or arrived. Now, by task scheduling, what we really mean is that the operating system or the scheduler part of the operating system will find out which task to be executed next, or in other words, what is the order in which various tasks are to be executed. So, that is the basic task scheduling problem. We have a set of tasks which keep on arising or arriving at different points of time due to events, and as soon as the events occur, the tasks arrive, and what is the order they will be executed. That is a basic problem. We will see, there are many ways this can be done. One, as he says, is that some priorities can be assigned, that is just one way. Let us see. And as I was saying you earlier, that this actually for a real time operating system, this is a crucial component, and in any course on a real time operating system or a real time system, you will see that task scheduling is a major portion of the course. Various types of schedulers suitable for various applications, and analysis of task behavior, task characteristics to find out a suitable scheduler. So, these are important problem here. First is to understand the different types of schedulers, to find their characteristics, the scheduler characteristics and the situations where they become applicable, and to find out which type of tasks will be handled, I mean which type of situation tasks will be handled by which type of scheduler, and we will do some analysis that whether it can really meet the timing constraints of this set of tasks and so on. Quite a bit of theoretical background is also involved here. Let us look at that. So, this is another term that we will use is task instance. Each task occurs a large number of times. For example, the temperature sensor might sense the high temperature at various points in time, and therefore, the same task will be fired again and again, and each time the task is fired, we say that a task, new instance of the task has occurred. Each time the task recurs, a new instance of the task is said to have been generated, and we will use the terminology, if T is the task, the ith time it recurs, we will use Ti. Now, this is another terminology and concept here that we will be using. There are two kinds of deadlines that we will talk of when you discuss about the schedulers. One is the absolute deadline and the other is the relative deadline. So, this is the task has got released here or arrived here. See here, T is the time at which the task has arrived or is released, and the deadline is D, and this is the relative deadline is between the task arrival to the instant of time at which it needs to complete. So, T minus D, or we will call it R, is the relative deadline, whereas the absolute deadline for this task is D. So, that is D is computed from 0, right. So, we will distinguish these two terms sometimes.
Time 0, whether it refers to the some like when we power on the system.
Exactly, exactly. The 0 time refers to when the system was started, and that it continues for a long time, maybe days, months. Right? 0 is the time of system start.
When it is actually powered on.
Exactly. The system becomes operational. That is the time, 0 time. So, is absolute and relative deadline okay? Relative is with respect to the task arrival and absolute is with respect to 0 time. Now, we will also use this term response time, which you had also possibly come across in operating system course, that when the task has arrived here, and then after some time it has started executing and it had completed by t, let us say. The task arrived due to a event e at, okay, let us say time e, although it is not a very satisfactory name here, e is the time, we should have written t or something. Anyway, so if t, okay, let us say that it is t, if the task starts at t, the task is released at t e or arrives at t e and actually starts executing sometime later, because the operating system will start the task at some time later, and then it continues executing, let us say, without getting interrupted, and finally completes at t. So, the response time is the time from where it arises or arrives and the time it completes. Looks okay? Okay. For the operating system, basic operating system course, we had seen that the, yes, previous one, yeah, please, yeah.
This time, is it also for the turnaround time? What we are not able to differentiate here. When we submit the task,
okay,
and then it is completed.
Okay, yes, yes, turnaround. No, the entire thing. See, you submit the job, and the time it completes is the turnaround time, but that's also equivalent terminology.
But here we are with respect to the event we are seeing.
No, there also, see, event is the one which actually, like he says, is submits the job, right? Here also, exactly. Here also, event E has created this task.
But that we are starting from a bit late.
No, there also, see, you submit a job, like let us say you press the key to start a task. Now, the job has been submitted by pressing the key, and then it takes some time to complete. It is the turnaround time, he says, for the task, and we use the response time, because we are, I mean, equivalent terminology, but what we are trying to mean here is that once a event occurs, what is the response of the system by which it produces the action, right? The task is let us say the temperature, high temperature is sensed here, and then it takes up the task of handling the high temperature sometime, because some other task might be running here, it cannot immediately start it, starts it after some time, and then as soon as the handler task completes, it finds that the shutdown switch should be, shutdown signal should be generated, and at this point the shutdown signal gets generated. So, the system took e to t minus e time to respond to the event, right. So, this is the terminology we will use, but there are other equivalent terminologies in operating systems. We will not use those terminology. In a traditional operating system course,
sir, but the time to respond is immediately, no sir. It has responded immediately, but the time it took is that much, t minus t. Respond is immediately.
No, we are requiring the system to respond within certain time, and then it responds in its own time, which may be less than the expected time, then it is doing fine. If it is more than the expected time or the deadline, then the system has failed, or it has, we need to do some handling of the exception that arises due to that.
Response time when it gets fast executed or till the completion?
Till the completion. See, after the completion only, then the action will take place. Let us assume a simple case where the action takes place only after completion. So, if the action can take place, like let us say once the task is running and it takes actions at different points of time when it is running. So, then that is a separate case, right, more complicated case that we are not talking of here, just considering a very simple case, that once the task starts, it does some computation, based on the computation it generates a signal, and the time from the event that occurred to the task that ran and completed and produced the signal, that is the response time. Okay. Now, in the traditional operating system course, implicitly, without, I mean, we discussing there that what kind of tasks we are running there, those are all soft real time tasks or interactive tasks, right. The user submitted a job like he said. So, in those situations, one of the objective of the operating system is to reduce the response time or minimize the response time, and that is the main principle by which all the scheduling algorithms for a traditional operating system like Unix or Windows is designed, to reduce the response time for the tasks. On the other hand, the kind of scheduler that we will see here for hard real time tasks is that we do not gain anything by completing it very fast. Minimizing the response time is not really very important here. As long as we are able to do it within the deadline, we are as good as completing it very fast. So, no advantage of completing any task early, need to complete it by its deadline, that is the only requirement. So, we are not worried about minimizing the response time. So, that is one important point must remember as we proceed further. We had also seen that the tasks are periodic, sporadic or aperiodic. There are three main types of tasks that we will be talking of. Periodic occurs after a time interval, somehow some clock is set, gives a interrupt, and most of these events, periodic events, are polling in nature, and we will see that a majority of the tasks that will be concerned are actually periodic tasks. And in simple systems like let us say air conditioner, so it is sampling the temperature periodically, let us say, and then as soon as it exceeds some value it switches on, right. So, this periodic events are many and many examples of that is there, and in simple systems most of the almost all events, 100% of the events in some systems are periodic in nature. Whereas, we will have few systems which are few tasks which are sporadic, occur at random instants, and aperiodic which again occur at random instant, but the minimum separation can be 0. Now, let us look at for a periodic task, what do we mean by the phase of the task? This is also a term that we will use very frequently. Once the system starts, the system is switched on, then after a delay of certain time, a periodic task starts and keeps repeating with a period of p, right. From this point, the first instance of the task starts, and then every p it keeps on recurring. So, this phi, the time phi for the first instant of the instance of the task to start from the 0 time is called as the phase of the task. Is that okay? We will use this term frequently. Let us consider an example of a phase. Let us say that a rocket is launched, and for 2000 milliseconds nothing happens. I mean, this task is not started, the track correction does not start until 2000 millisecond after the blast off of the rocket. The track correction does not occur within 2000 millisecond, but then this track correction task recurs periodically every 50 milliseconds from that point, from 2000 millisecond onwards. And then this task might have some characteristics that takes some 8 millisecond to run, deadline 50 millisecond. So, this is the characteristic of the track correction task, but till 2000 milliseconds, which is the phase, the task does not start. The first instance starts only at 2000 millisecond, and then at every 50 millisecond the track correction task is released or arrives. Now, few more terminologies, because as we are saying that in any area, whether you are talking of a doctor or you are talking of a computer person or you are talking of a mechanical person, mechanical engineering person, everybody has his own terminology, every area. So, if we get familiar with the terminology, we will understand the topics well, and if we read a literature or a book, we will be able to appreciate that. But of course, terminologies are a bit boring, you know, you have to remember what are these terms and what is their meaning. One is a valid schedule. A valid schedule is a schedule produced by the scheduler. We will call it as a valid if at most one task is assigned to a processor. If we have a single processor, okay, not a problem. If we have multiple processors, okay, even in a single processor, if at the same time 2 tasks are given to the processor, right, that is not a valid schedule. And also no task can be scheduled before it is ready. So, first the event should occur, and then we have a valid schedule. And all the precedence and resource constraints, I have not discussed this till now, we will come across this as we proceed. The precedence and resource constraints are satisfied, then we will call it as a valid schedule. But a valid schedule may or may not be a feasible schedule. A feasible one is where the timing constraints are met. See, here we are nothing talked about timing constraints. If the timing constraints are met, then we will call it as a feasible schedule. There can be many feasible schedules. Now, as of these we have to select the best schedule, right, and then in this case we have the proficient scheduler. It produces a better schedule. A proficient scheduler produces a better schedule. So, a scheduler S1 is as proficient as another scheduler S2 if the set of tasks for which S2 can schedule it, S1 also can schedule it. So, S1 is as proficient as S2. So, that means whatever S2 can schedule, S1 can also schedule, and vice versa. Okay, okay, it should have been vice versa, and vice versa, because it is as proficient.
No, sir. It is not vice versa.
Okay, it is more proficient. Okay, I think there is a the term is slightly misleading. If we had said more proficient, then this problem would not occur. So, proficient means it is more proficient. So, okay, here is the main problem here. S1 is more proficient, it is not as, right, there is a mistake here.
That is at least as proficient as it, at least as it.
Okay, S1 is at least as proficient as another, or S1 is more proficient than another. It is at least as proficient. I think that is a correct term to use here. So, S1 is as proficient as another scheduler S2. If S2 can handle a set of tasks, produce a feasible schedule for a set of tasks, then S1 also can produce. An equally proficient scheduler on the other hand is one where if S2 can produce a feasible schedule, so can S1. And we can extend that terminology to talk of an optimal scheduler. This terminology we will use very frequently. Here an optimal scheduler is one which can feasibly schedule any set of tasks that any other scheduler can. Any other scheduler can produce a feasible task, then the optimal scheduler should be able to produce the feasible schedule, right, is the concept of optimal. It is a valid and also feasible, that means time constraints are also met. Or in other words, if any scheduler can produce a schedule by which the time constraints of a set of tasks is met, the optimal scheduler can definitely do that. But sometimes some scheduler will fail to produce a schedule for some set of tasks, some combination of tasks, but the optimal scheduler in any case will produce the schedule if any other scheduler is able to schedule. I am not saying that the optimal scheduler will be able to handle all cases, no. Many of the tasks it may not be able to handle, right, it may not be able to produce a feasible schedule for many types of tasks, but it is at least as good, or it can at least produce the feasible schedules what the other schedulers that are known can produce. Is that okay? Okay, so let us stop here. We will continue in the next class.